So, okay. Well, before I introduce our speaker, I guess I want to say that the CCPR committee will be sending an email soon to ask everybody for their feedback for next year's seminar. So we'd love to hear from you. If you have any ideas about who you want to see next year, please let us know. So that's going to be coming your way. And I also want to remind people that we sent out an invitation to submit suggestions for the Rob Mayer Student Lecture that takes place annually. And we like to honor our students. We have great students. So if you are a student and you want to present, or you have a student who you'd like to see at CCPR, who's graduating this year, who's been a member of CCPR, please send us your nominations. So with those two announcements made, would love to introduce Silvia Barcellos, who is our speaker today. Silvia is at USC, and I'm really delighted to have her here. She was my student at Princeton many years ago, and I convinced her and her husband to move to sunny California. I've collaborated with her, and I'm still collaborating with her on research. So I am very excited to have her today talking to us about whether education is the great equalizer, which I'm very, very interested in, and I hope everybody else will be very interested in as well. So Silvia, take it away.
Sure. Thank you, Adriana. Thank you for the invitation. I'm very excited to present this work. This is among one of the first times that I present this, and this is, I think, my first actual Zoom seminar. So it is very different, but I hope, it's gonna be okay. So this is joint work with Leandro Carvalho, who's also at USC, and Patrick Turley, who's at the Massachusetts General Hospital. And we ask, the question we're asking is education the great equalizer, right? Many people have this view. So I kind of added two quotes here. The first one by Horace Mann, saying that education then, beyond all other devices of human origin, is a great equalizer of the conditions of men, the balance wheel of the social machinery. And then one much more recent by the US Secretary of Education in the Obama administration that says, in America, education is still the great equalizer. So in this paper, what we're going to do is to see if there's any empirical evidence for this idea of education being the great equalizer. In particular, we're going to ask if education equalizes differences in two proxies for at-birth endowments, birthplace and genetics. So both birthplace and genetics are very strongly associated with later life SES, and education is seen as a way to possibly help people overcome such types of initial disadvantages. In a series of very prominent papers, Chetty and co-authors find that the neighborhoods where children grow up really affects a lot of their later life outcomes, such as earnings, college attendance, fertility, and marriage patterns. And these effects, so children who live in neighborhoods of better quality, they usually get better, later life SES. And this effect is especially strong for children coming from poor families. Genetics also has been shown to be very highly associated with later life SES. For example, there's been a large-scale genetic association analysis of educational attainment, and it shows that a polygenic score, which is an individual level index of genetics, can predict 11 to 13% of the variation in educational attainment. So the question we're going to ask here is then, in this world where initial endowments matter so much, can education level the playing field? Can it equalize opportunities of economic success? So we're going to ask in particular whether education reinforces or equalizes or mitigates these strong associations between initial endowments and later life SES. Well, in theory, these associations, these effects could go either way, right? On one hand, education might compensate for individual disadvantages, or there may be diminishing marginal returns in the production of socioeconomic status, in the sense that, you know, and then education could be equalizing these differences. On the other hand, returns might be higher in neighborhoods with more economic opportunities or better schools. We know that it's not only the quantity of education that matters, but also the quality of education. Or it could be that, you know, smarter people, smarter under codes, might benefit more from a given amount of education, in the sense that instead of equalizing, education could in fact increase these gaps, increase these disparities in terms of initial endowments. So what we do in this paper is that we're going to use a compulsory schooling reform as a natural experiment. And the compulsory schooling reform has kind of two, in this context, has two advantages. One, it gives us what economists call kind of an exogenous source of variation in education, meaning that it gives us some increase in education that was not chosen by individuals. And it also, it's interesting to look as a reform because compulsory schooling laws are among the most common types of educational reforms around the world. So when countries want to raise their level, their population's level of education, they very commonly use, you know, either limits on how old kids need to be in school or how old kids need to stay in school for. So it's kind of this question about, it's not only about education, but about what real policies that can affect education. What do they do in terms of addressing these disparities in terms of initial endowments? So we're going to use the 1972 ROSLA in the UK. This is it's called like ROSLA is called Raising of School Leaving Age. So what this reform did is that it increased the school leaving age from 15 to 16. So it's an increase in secondary education. And interesting for our purposes, it increased for students born on or after September 1st, 1957. So this is interesting because we're going to see that it kind of generates a very stark pattern in education, what we call the discontinuity in education, that we're going to use in order to estimate the causal effects of education on wages later in their lives. So I'm going to show, and it's also been documented by other papers, that this reform increased schooling and wages. But not only that, I think what the question we're interested then is to ask how the returns to education induced by this policy vary with our proxies for initial endowment. So we're going to look at place of birth. In particular, we're going to get historical data and get at the SES of the person's place of birth at time of birth. And then we're also gonna look at genetic predisposition to educational attainment, which I'm gonna explain later how we construct that. The interesting thing about these two proxies is that they are determined at birth and strongly associated with later life outcomes. And we're going to ask, does education affect the association between these endowments and SES later in life? And if it affects, does it reinforces it or mitigates these types of associations? So I should say, I welcome questions if you have any, just, you're welcome to talk. It's just that I'm, as presenting, I'm not gonna, I can't look at chats or so. Just you're welcome to interrupt me at any time. So I'm just gonna talk very briefly about some related literature. There's been a number of papers that use dynamic structural models to get at the returns to schooling and how they vary with cognitive and non-cognitive skills. Usually these papers find that the returns to schooling are higher for people with both types of higher skills, especially when we're talking about returns in terms of pecuniary returns, or returns for education in terms of earnings. There's also related literature that looks at returns to schooling and how that vary with geographic measures of school quality. There's a seminal paper by Card and Kruger that estimates at the state level that men born and educated in states where measures of school quality are higher, such as teacher pupil ratios or teacher pay, have higher returns to to a given extra year of schooling. And then there is a third literature that doesn't really look at kind of differences in returns to schooling by genetics, but looks at genetic heterogeneity in earnings and wealth. And they document that this type of polygenic score that I'm going to be using here for educational attainment actually it's a very good predictor of effects, say wealth at retirement, even controlling for education and labor income. So, it really shows that, this polygenic score is capturing something very intrinsic and some sort of decision-making ability by individuals. So in terms of where our paper fits, I think our paper is much more on the, say, reduced form approach than the more structural approach. We have a very nice source of exogenous variation of education. We have a very nice regression discontinuity result, and a large sample that allows us to have well-powered estimates of the interactions between education and this individual and this initial endowments. We also have, I think the other thing that is distinct is that we're really focusing on initial endowments. So things that are predetermined, determined at birth, as opposed to some of these other measures of skills that are not, they're measured later on in kids' lives. And then finally, we have, we combine this type of reduced form, natural experiment approach with these novel measures of genetics. So I think a lot of people have used, natural experiments to look at questions related to return to schooling, and some, and now with the recent advances in behavior genetics, there's been more and more papers looking at the effects of genetic variables on schooling and SES. But we are in this nice intersection where we're using the natural experiment with the genetic data. So just to preview some of our results, we find no evidence that education is the great equalizer. We do see that the compulsory schooling reform reduced differences in education by endowment. So by forcing people to stay in school until age 16, the reform affected disproportionately people from the lower bottom of the distribution of endowments. Yet we see that it increased differences in log wages later in their lives by these endowment groups. And the widening of such gap was even starter among compliers. So we see that there's a difference between 5 to 7 log points in terms of our main outcome is going to be log wages. We see differences of 5 to 7 log points in the returns to an additional year of schooling between those in the top and the bottom terciles of the endowment distribution. And these results hold independent of whether we use genetics or place of birth, or both as our measures of endowments. So if there are no questions, I'm gonna go ahead and talk about the data we use. We use data from the UK Biobank. The UK Biobank is a large study, national study initiated by the NHS in the UK. It interviewed 500,000 individuals ages 40 to 69 during between 2006 and 2010. So the data was collected about 34 to 38 years after the introduction of the ROSLA, the reform we're gonna study. And the data has some interesting features for our purposes. First, it has exact date of birth. So it really helps the precision of our regression discontinuity design. It genotyped the whole cohort of people, so we can calculate these individual level genetic indexes for all participants. And they also report the approximate coordinates of birth for each one of the participants. So what we do is that we link coordinates of birth to historical data on neighborhood SES around time of birth. So we're gonna have things like average education level, average occupation SES, average mortality at each neighborhood of birth around time of birth. So this is gonna be we're gonna use this for our measure of birthplace quality. So on the negative sides, this reform is, this data set is not nationally representative. In particular, the participants have been shown to be better educated than the overall population. However, we see that we see no difference in the, in the pre and post threshold of the reform that we're going to use. So we do believe that our results have internal validity in terms of looking at the compulsory schooling reform. And also the data set has somewhat crude measures of SES. And in the next slide, I'm gonna tell you how we get around that. It has a great measures of health, but not so good measures of economic measures of SES. So we do restrict the sample in a few ways. First, we restrict the sample to participants of European ancestry, and that's because those are the population for which the genetic indexes that we're going to be using are valid. This is not a big restriction for the UK in this cohort, because there's not a lot of people without European ancestry in this cohort, but still we miss a lot. We throw away about 5% of the sample. We also look at people born in England, Scotland, or Wales born between 10 years of the reform threshold, which is September 1st, 1957. And who left, and so that's just because this is kind of the population to look at the most applied to look at the compulsory schooling change. And finally, we restrict our sample to people who left school at age 18 or younger. And that restriction has two reasons. The first reason is that in the UK Biobank, we don't really have the school leaving age information for people who went to college. If you went to college, they don't ask you what time you left school. So that kind of has some measurement issues in there. And then the second reason is that in our data and in other, and this has been documented by other papers also, show that the compulsory schooling reform doesn't really affect the probability of staying in school past age 18. So we see that, it's not like they require you to stay in school until age 16 and then suddenly now you're going to college. No, we see most of the effect on people staying in school until age 16, some effect on people staying until 17, a little smaller effect in staying until 18, and nothing after that. So by focusing on this population, we're really focusing on the population who was most affected by the policy. So once we get all these restrictions together, we are left with about 100,000 observations for our main sample. So I told you that the UK Biobank doesn't have really good measures of SES. The best measure they have is occupation. In the verbal interview, respondents reported their occupation, and answers were coded in more than 400 detailed occupation categories.
Excuse me, this is Don Tryman. I don't know whether you can hear me.
Sure, yeah, I can see you.
Okay, I'm sorry. I want to, before you get to the occupation, I have a question. Could you describe the creation of the polygenic scores? That's a very large sample. And so it would be interesting to know what process or what, who created those scores?
Yeah, so I'm gonna go in detail on that in a few slides. But we created the scores with some data that is some summary data from different GWAS, right? From different genome-wide association studies. So I'm gonna go into more detail on that just in a few slides. Okay. So back to SES. So we are our main outcome then. We're gonna use the 2009 annual survey of hours and earnings to match such categories to median wages for each occupation. So because we need a way to rank these occupations, we thought, and we are economists, we thought, oh, the best way to rank them is wages, right? So what we did then, we got gender-specific wages calculated among full-time employees and including all labor incomes, such as bonus, tips, and overtime. And we created this 400 plus categories, and we matched them, these wages to each occupation. And I'm gonna refer to this measure going forward of occupation-based wages, that's simply wages, and this is gonna be our main outcome. The nice thing is that, one nice check that we did is that, is that we have household income in brackets in the UKB. So these are kind of the brackets in this figures are the brackets that people report their household income in. And what we did is that we graphed the cumulative distribution of log wages by these household income brackets that people report. And so this is a nice check because those are these occupation matched wages. And they show a pretty nice pattern with the income thresholds, right? As you'd expect, those reporting lower incomes have a distribution of wages to the left of those reporting higher income. So we thought that was a nice check of the data. So before I talk about like the different measures of heterogeneity, including the genetic heterogeneity, I'm going to talk a little bit about the raising of school leaving age, the compulsory schooling reform that we use. So in 1972, England, Scotland, and Wales raised their minimum school leaving age from 15 to 16. And the policy only affected students born on September 1st, 1957 or after. So students born before that could still drop out at age 15. So this is very nice for our empirical strategy, just because students born within days of each other who would otherwise have had similar education and SS ended up with differences in schooling. So here's kind of the graph that shows you kind of the average differences in schooling. You can see it's the average school leaving age on the y-axis by quarter of birth in the x-axis. And you can see that school leaving age was already increasing by cohort before the reform. But on the vertical line, which marks the September 1st, 1957 policy threshold, you see a jump, right? You see that these students who were born right after this time got on average about a third extra year of education than those born just a few days before. So this is interesting because what we'll be able to do is to look at this very distinct data pattern and ask, if we look at wages during their midlife, when they're 50, and we look at the pattern of log wages, do we see such a jump? And if we see such a jump, we're gonna interpret that as the causal effect of education on wages. So this is kind of like just the intuition behind this regression discontinuity design that we're gonna use to study the causal effect of education. And the main identifying assumption behind this design is that people on either side of this threshold are on average similar, except for this extra education. It is an assumption, so it cannot be fully tested, but actually the genetic data are useful to offer support evidence, because the genetic data is objective, determined at conception, and immutable. So if we see that these respondents are genetically similar on both sides of the reform threshold, then that's pretty good evidence that this identifying assumption holds. So that's exactly what we do. We look at different genetic markers and we see, do we see any jumps at the reform threshold? So the educational attainment polygenic score is the second graph on the top, graph B. And you can see that we have a BMI polygenic score. We have the PCs are different principal components of the genetic matrix. And we can see that, there's basically no jump in any of those. We look at, all the different PCs and we test them individually and separately. And we basically see no statistically significant difference. Also, we look at other predetermined characteristics, such as where you were born, the coordinates of birth, if you're left-handed or right-handed, if you're adopted, and we see nothing.
How do you explain the decline, the negative slope on education? It's not here now. You went down, but
this one?
Yeah. No. Back to your set of.
This
yes,
one.
Those.
The polygenic score.
B. What? Yes.
Yeah, that's a good question. I wouldn't say I don't know if this is significant, but I'm gonna test. And there's a bit of a positive on the BMI and a bit of a negative on the EA. Yeah, I'm gonna test the slope. Yeah, good point. Yeah, thanks. The other thing that could happen, the other way to kind of like get at this identifying assumption of the RDD is to ask whether, it could be that, the reform affected education, and education might have affected the probability of being in the UK Biobank. So what we do here is that we do what's called the McCreary test, and we are going to ask whether we see discontinuities on the density or on the number of observations at the policy threshold. And you can see then, the p-value is 0.22. There's no evidence. This is by day of birth. So this is what kind of the distribution of the number of outcomes, the number of participants by day of birth look like. So, we pass all our kind of tests for the identifying assumption. So what we do then is look, okay, is there an effect on wages? And again, as has been documented by other papers, we do see that at the threshold, at the policy threshold, we see a positive jump in log wages, suggesting that the reform increased log wages among the whole population by around 1.7% or 1.8 log points, right? So here's kind of like just a little summary of what the reform did for this cohort without looking at the heterogeneity. The reform, what we call the first stage is the effect of the reform. So post is an indicator for being born after September 1st, 1957. And we saw that it increases education by about a third of a year. Then the OLS shows you kind of just the OLS correlation between log wages and school leaving age, which in this population of people who left school by age 18, it's about 6%. So one extra year of schooling gets you 6% larger wages. And then the reduced form is the effect of the reform on wages of the whole population, it's about 1.8%. And then the two-stage squared is what we call the effect among compliers, or the effect of 1 extra year of education on wages. And it's interesting, it's about 5.6%, which is very similar to the OLS estimate. Okay, so this is all to say, this is a reform, it's been studied in the past. It affected, it looks good in our data, it affected education, it affected wages. But now, of course, what we're interested is in how is there any heterogeneity in how it affected these returns, right? Do we see that people from with these differences in addition endowments are different? And here's where, I'm going to talk about the polygenic score for educational attainment. So what we're going to be using to look at genetic heterogeneity is we're going to use the individual level data in the UK Biobank for genetic individual level data to construct these linear indexes that predict educational attainment based on genetics. And these are called polygenic scores. And in our case, polygenic score for educational attainment. So what a polygenic score is just a way to summarize all the information in genetics, which is pretty large, into one index. So what the research in behavior genetics have found is that there's no one gene for education, right? Or one gene for any behavioral factor. There are many genes that help predict education, and all of them have a very small effect. So the nice thing about the polygenic score is that the polygenic score kind of aggregates all these effects into one index that is much more that has much higher predictive power than if we used one single gene. So just to answer the question now, so how exactly do we construct this polygenic score? So a polygenic score is going to be a weighted average of a person's genotype. So S is going to be the score for individual I. GYJ is going to be the number of minor alleles at SNP-J. So SNPs are the parts of the genome where people are different, right? So the parts of the genome that vary from person to person. It's kind of like the parts that what makes us unique, right? Most of our genome is identical across humans, and then there are few places in the genome where we differ. And the SNPs are like some of these places where we differ. So we're gonna ask, how is this person different? And then we're gonna assign a weight to each one of these SNPs J. That's gonna translate what this SNPs means for predicting education. So the weights come from what we call genome-wide association studies, or GWAS. So what these GWAS do is that they span the whole genome and they look for which genetic variants are associated with a certain outcome, in our case, educational attainment. And then what we do then they calculate this polygenic scores. And in our case, we're going to use this GWAS by Lee and al. By 2018, for which the polygenic score explains about 12 to 13% of the variation in educational attainment. So just coming back to the question that was asked earlier, what happens here is that, we have the G's, by the GYJs for our data. We're gonna get these W's, these weights from GYs that do not use our analytical data. So that's why we had to construct these weights ourselves, because we wanted to, because the UK Biobank is such a big part, such a big sample, we wanted to construct weights that took into account the UK Biobank, but did not use our sample, our analytical sample, because we wanted to avoid overfitting and things like that. So that's how we construct these scores. If there are no questions about the construction scores, I'm going to talk a little bit about how we should interpret these results, because there's usually a lot of confusion about how to interpret polygenic scores. I want to really highlight here that these polygenic scores are associations. They should not be interpreted as the causal effects of genetics on education, and they're not capturing only direct genetic effects. They're really capturing anything that can be related or affected by genetics and have many pathways. So one obvious, right? If we think about, yeah. Go ahead.
Earlier question. This is Don Tryman again. In my earlier question, I was really asking about the sampling procedures to produce the biobank. Could you tell us a bit about that?
The sampling procedure. So what they did.
What kind of sample it was? It was a very large sample.
Was a very large sample. So what they did is that they mailed invitations for like over 9 million people ages 40 to 69 that were registered with the NHS in the UK, which is, I think, above I think 98% of people are registered with the NHS. And they mailed people these letters, these invitation letters for people who lived around, I think, a few miles of the 22 assessment centers. They had like 22 assessment centers all over the UK. And they only invited people who lived, miles of those assessment centers. And then the reply was, I think, like 6%. That's the response rate. To get the 500 respondents. So again, this is a very large sample. They put the assessment centers with an eye to have some variation, to have some variation in the sample. So they try to have to oversample like difficult populations and things like that. But it's in no sense it's a nationally representative sample, if that's what you mean. So it's a very diverse and very large sample, but it's not nationally representative.
Thank you.
Okay. So just to go to like this genetic.
Silvia?
Oh yeah, sure. Go ahead.
Sorry, Adriana here. Just to follow up on that question. So is the predictiveness of the polygenic score the same in your sample as in the GWAS studies that produce the weights?
Yeah, so that's it's a hard question because of that issue with the school living age. We have kind of a truncated measure of education, right? Because we don't have years of schooling we only have years of schooling until age 18 or something. But we've looked at things like college. There's been even the paper that produces, I think, the Lee and al. Paper looks at some outcomes and it looked pretty. It's very predictive. I'm gonna show some results here, and it looks in line with what they see in other samples. That said, the big samples are all not nationally representative, right? A lot of these large samples that are used in GWAS are not nationally representative. Just now, we are starting to get things like the health and retirement study or the some other national, like ELSA in the UK, other nationally representative samples that are collecting genetic data. But for a lot of these earlier cohorts, they're not going to be nationally representative. So we did some work comparing the distribution of our PGS to the distribution of the PGS in the ELSA, which is the aging survey in England. And we saw some differences, but they were not as stark. We saw, for example, that the support of the distribution fully overlaps. So it's not like we're missing part of the PGS distribution. It's just that it's differentially distributed, if that makes sense, within that support. So so just back to how to think about those. So it's important to think that the polygenic score may capture intergenerational effects, right? Like one obvious in the type of analysis that the construction of the PGS that I described to you, one obvious omitted variable is parental background, right? Parental background, your parents' genes are going to affect the genes you inherit, and also are going to affect their own characteristics, such as their education, and their education affects your education and your income. So there's this very nice paper by Kong et al. That uses a sample that has both the genetic of parents and offspring, and they show that even the genes that are not transferred to offspring, they affect offspring's outcomes. So here in this diagram you have the transmitted paternal genes, the transmitted maternal genes, the non-transmitted paternal genes, and the non-transmitted maternal genes. And they say they do what they have, like what the direct path is, right, to the transmitted genes that affect the offspring outcome. But there's also what they call the genetic nurturing path, which is the fact that these non-transmitted genes also affect the offspring outcome, right? And when we look at the polygenic scores that we're gonna be using here, they show that about half of the variance of educational attainment can be accounted by direct effect, and being the other half, meaning that the other half is due to this intergenerational or genetic nurturing path. So this is one thing that we must keep in mind, right? That when we're using this PGS, it's not just about the effect of your own genes or the causal effect of your own genes, but it's really something much broader that includes even family background variation also. The other type of omitted variable here is population stratification, right? If there is a certain outcome that is very common among a certain ancestry group, and this ancestry group has certain genetic, genetic structure, then when we do the GWAS, we're going to see that, this GWAS is going to be affected by ancestry effects. So the most common example of this is chopstick use, right? If we did a polygenic score for chopstick use, we would get a lot of hits of genes related to Asians populations. And it's not that Asians are have better ability with their hands, it's just because of a cultural effect. They're more likely, the cultural factor, they're more likely to use chopsticks. So what we're gonna do to deal with that is that we're gonna control for the first 15 principal components of the genetic matrix, which has been shown in the genetics literature to be a good control for this ancestry effects. So that said, I think that said, when we look at which genes are strongly active in the brain and involved, and which genes are strongly are related to this educational attainment, we find that they're strongly active in the brain and involved in neural development. So this slide is really to say this PGS indexes, they really reflect a number of things. Among these things is cognitive and non-cognitive skills, which are the things that at least economists usually think about. But you should, when looking at them, we should really think about not only about this, but a host of other pathways. So here's where I say, that in our sample, genetics is very correlated with later life SES. In our case, our measures of log wages. So this graph log wages in the y-axis and the standardized EA polygenic score in the x-axis. And for pre-reform compliers. So what are pre-reform compliers? Pre-reform compliers are the people who were born before September 1st, 1957, and who left school before age 16. So they're compliers in the sense that when the school, if the school hit them, they would have to stay in school until age 16. So these were the people who would have been affected by the policy. And what we see here is that people with like higher polygenic scores, even within our pre-reform compliers, have much higher higher wages, and that the numbers here are the coefficient, the standard deviation, and the p-value, and you can see that this relationship is highly significant. Here's just kind of the same thing. You know, we see that one extra, there are a lot of numbers in this table. I apologize, but this is only to say that in the whole sample, the first two columns, one extra standard deviation in the PGS increases is associated with an increase of about 2.7% in wages, and among our compliers, it's 1.8%, 1.6 to 1.8%. And again, this is, even our all sample is a sample of people who stayed in school only until 18. If I lift this restriction and I say, what's the, how is the PGS correlated with log wages among everyone, then this correlation is much larger. You know, an increase in one standard deviation in the PGS is associated with a 7% increase in log wages. So very, again, kind of back to the point that these initial endowments matter a lot in this context. So one thing that we talked about is how, you know, how this PGS might reflect family background, right? And in the UK Biobank, there is a group of about 20,000 siblings. So what we do here is that we ask the question, you know, how does the PGS predict school leaving age and log wages among within siblings? If we look at siblings fixed effect specification, if we take away the family, any kind of like family fixed effect, right? And the first, so if you look at the first three columns, they're for school leaving age. The first column shows like the OLS for everyone, and again, we see the result that we just saw in the previous slide. And then for the OLS for the SIBS sample, so it seems like it's a bit higher in the SIBS sample, and then the SIBS fixed effect. And what you can see there is that, like, very, even though it's not significant, I think it's because of the much lower sample size that we have, but we have a very similar result to the Kong et al. That once we add kind of sibling fixed effect, or we take into account parental genetics, the correlation drops by about half. So this is kind of, I think, very in line with what we see in the Kong et al. And then surprisingly for log wages, we see that actually, we don't see that when we go from the second to last column to the last column, we see that when we add these fixed effects, we don't see a decrease at all. So that the polygenic score is predictive of log wages even within siblings. So again, this is for you to help you think through what these polygenic scores are reflecting. I think they are reflecting a lot of family level variation, but also they're definitely also still have some individual level variation, that these correlations are still significant even within families. So this is, I'm gonna move now to birthplace heterogeneity and our measures of neighborhood SCS. As I mentioned before, we used approximate coordinates of birth in the UKB to match to historical data on local authority level SCS in 1961. So it's around the 1957 birth cohort. We have about 1,600 such neighborhoods, and each one of these neighborhoods has about 39,000 people living, with a median of 19,000 people living in each neighborhood. So just to give you an idea, the Chetty et al. Use about 741 commuting zones with an average of 380,000 people in each. So in a sense, our neighborhood is much more of a neighborhood than those bigger geographical areas. So the variables we have at this level are the percent of people at different education levels, the percent of people with different occupations, and home ownership and mortality. Today, I'm going to use results. I'm going to show you results using the number of people staying in school until age 15 for each one of these neighborhoods as kind of a measure of quality of SES. And we've done some work that showed that this kind of, even though it's not as good as, say, a dummy, like fixed effect, you know, like local birthplace dummies, it captures a lot of this potential variation by neighborhood at this level of aggregation. So, and again, I can show you that, you know, among compliers, we have a positive, this is kind of a similar thing that I graph to the one I showed you for the genetics. We see that for the among pre-reform compliers, those who live in better, who were born in better neighborhoods tend to have higher wages, even though this among compliers, the p-value is about 0.11, so it's not significant. But again, if you look at the whole sample, so if we look at the two first columns in this table, we see again that a 1 standard deviation increase in the regional education level is associated with about a 1.8% increase in law wages. So again, and again, if we drop the restriction that people need to be born, to stay in school, to leave school by age 18, these associations are much higher. So again, these are initial endowments that really matter for later life outcomes. So next so I showed you how the reform affected school leaving age, right? So next I would like to show you how the reform affected school leaving age for these different groups of initial endowments. I'm gonna start with the educational attainment polygenic score. And again, as you would expect, even before and after the cohort affected by the reform, we see that those with higher polygenic scores, you know, these are the kind of polygenic score terciles, higher polygenic score terciles is the one with the most genetic predisposition to education, medium and low. So you can see that the higher the polygenic score, the higher the school leaving age, right? So that would make sense since those are scores that are constructed to predict education. What we can also see in this graph is that when the reform hits on the line marked by the vertical line, all the three groups jump. So we see that the reform affected education of all the three groups, but it affected the education, the jump was largest for those with low polygenic score. And that's simply because those people were much more likely to drop out of school before age 16, before the reform. So the second group, the second graph that I'm showing you, in the y-axis, instead of average school leaving age, I show you the fraction leaving school at age 16 or later. And you can see that the fraction leaving school at age 16 or later is much lower for those with low PGS. So this is a very nice way to see what the reform did. So what the reform did is, you know, you had this variation on people, on the fraction of students leaving school before age 16, and then the reform made everyone stay in school at 16, so it kind of contracted this, it kind of like made this gaps disappear, right? So in this sense, the reform did equalize education across these endowment groups, because it made groups that had very different probabilities of leaving school before the reform all stay in school until at least age 16. And we see very similar patterns when we look at neighborhood of birth. Here's the average school leaving age. We see that average school leaving age was higher for those living in high neighborhood, that were born in high quality neighborhoods. And again, when we look at the fraction leaving school at age 16 or later, we see that those from low quality who were born in low quality neighborhoods were much more affected by the reform. And this is just kind of the table for this graphs that I showed you. You know, the post tells you kind of that the reform affected on average, increased school leaving age by on average a third of a year. Those with higher polygenic score and from higher Reg Edu 15, which is the quality of your birthplace, have higher, stay in school longer. But then when we look at the interactions between the PGS and the post and the Reg Edu 15 and the post, they're negative, meaning that those with lower PGS and lower Reg were most affected by the reform. So given this reform, now we come to the point where we want to answer our question, right? How did this reform then affected SES later in life? We already know that the reform affected those from lower endowments more, but what we really want to know is, do they get better off? Are they, this reform is helping them close some of these SES gaps that we saw in terms of these initial endowments. So I'm going to use two models to look at that. First, I'm going to run a continuous model where my dependent variable is going to be log wages, and I'm going to interact school leaving age with the score plus, and alpha 1 is going to be my coefficient of interest. Then I'm going to have the score and the school leaving age and those date of birth trends, right? So the FDOB are going to be polynomials in date of birth. They're gonna control for cohort trends. And I'm going to do that for the interaction with the polygenic score and also the interaction with the birthplace education. And I'm going to instrument for school leaving age using an indicator for whether the person was born after September 1st, 1957. I'm going to show these results graphically. I'm going to plot lines where I'm going to plot alpha 1 hat SI plus alpha 3 hat against SI, and the same thing for Reg Edu. And then my second empirical specification is going to be a discrete model where I'm gonna divide the sample into bottom, mid, and top terciles for the polygenic score distribution and the Reg Edu 15 distribution. And I'm going to ask how does log wages are differentially affected if you get this school leaving age by school leaving age differences if you're in the bottom, in the mid, or in the top tercile. And I'm going to plot like 3 bars, 1, 2, 3 against kind of medium for each tercile. So these are kind of our main results. So these are kind of reduced form effects by polygenic score. And again, the line is the continuous model and the bars are the tercile models. And this is the reduced form, meaning that it's the effect of the reform in the whole population. And what we find is that surprisingly, somewhat surprisingly, even though it's those that I showed you that those in the bottom per tercile of the PGS distribution were the most affected by the reform, it's those at the top PGS that had the largest increase in log wages. This relationship is highly significant. So we have, a p-value of 0.0037. So it's highly significant, and the interaction is positive. We see something similar for the neighborhood. It's not as large in magnitude, but it's still pretty significant, and it's not, and the terciles are not monotonic. But again, we have this curious result where even though it was those who were born in, say, worse quality neighborhoods who had the largest increase in education, but they don't seem to be the ones gaining the most in terms of log wages. And this is surprising because these reduced form effects are effects among the whole population, right? Within each one of these groups. So here are the reduced form effects in table form. And again, you know, the PGS post and the Reg Edu 15 post results are significant, you know, especially the Reg Edu 15. So I should explain more, like we have 2 columns for each specification, if you want, because we have one column that is a bandwidth of 4 years and the second column is a bandwidth of 10 years. The 4 years one, we have linear trends, and the 10 years one is we have quadratic trends. And what we can see is that the results are pretty robust to having like larger, smaller bandwidths and the type of trends. And again, the interactions between the genetic score and the birthplace quality are positive. And in the last 2 columns, we add both interactions in the same model, and what we can see is that the results are pretty much the same, suggesting that you know, we have these 2 interactions are somewhat independently working. So it's not like the polygenic score is loading the birthplace interactions or vice versa.
Sylvia?
Yeah.
So some of these are kind of marginally significant.
Yeah.
They're not really, but it strikes me that maybe what you want to report is a test that the interaction is negative, right?
Right. I'm gonna get to that. Yeah. There's no way we're gonna get to the fact that we see no we can reject that there's any negative interaction. Yeah.
Right. That's what we would like to know.
Right.
Like, kind of what is the biggest, so if you take these confidence intervals and you look at some of these confidence intervals include negative effects, like what is the most compensation
right
that could be occurring in here, and you it seems like you would be able to rule out in most cases any very large effects.
Right. Yeah, before I go there, let me show you the 2-stage least squares, because as you can imagine, due to the pattern in first stage, the 2-stage least squares effects are actually much stronger, right? You know, once we take into account that those in the bottom terciles are more affected. So these are kind of like 2-stage least squares effect of one, what would mean the returns on the log wage returns on schooling of 1 extra year schooling. It's about almost 10% for the top tercile, while it's like about 3% for the bottom tercile. And again, we see similar things for the neighborhoods. And as you can see here, the results are much more robust here in the 2-stage least squares, right? We see that, and again, if we include them all together in the last 2 columns, we see that they both survive independently. So next, I do exactly what Adriana suggests. So, well, not exactly, because she was suggesting in our school leaving age, in our sample. What I do here is you could think that, you know, we see these disparities, right? We see education increasing gaps for our sample of people who left school before age 18. But you could think that, you know, these people are still they're still benefiting from the extra education. They still have better outcomes. So it could be that for the population as a whole, when we drop this restriction, education could be an equalizer, because the compulsory schooling, what the compulsory schooling law is doing is that it's increasing the bottom part of the distribution, right? So what we do here is that we look at reduced form effects for the whole sample without making the restriction that people had to stay in school until age 18. And we ask exactly what Adriana was asking. What is the bound, right? What is the maximum of equalization that we can see? So what this figure shows is the difference in log wages between top and bottom terciles before the reform and after the reform. And you can see that for the EA polygenic score, it's about a 15% different in wages. And for the birthplace quality, it's about a 7% difference in wages. And you can see that they don't drop after. And even if you take, the bottom line of the bottom of the confidence interval there, you can reject any large reduction in this very large initial gaps. So this is kind of like a graphical way of getting at what Adriana was hinting. So then I think in the last few minutes that I have, I wanted to maybe talk a little bit about where can these results be coming from? And the first thing that we looked at is that maybe those people with higher scores, higher initial endowments, they react to the policy differently. So here, students in the UK have the option to take qualifications. They can take CSE or O-level qualifications. These are exams that are recognized and valued in the labor market. They can take CSE or O-levels when they are 16, and they can take A-levels when they are 17 or 18. And what we see here is that a number of students, even though they were not required, but then a number of students who were affected by the policy decided to take these exams, right? If you look at the SLA in the bottom of the CSCO level column, you can see that school leaving age did increase the probability of people taking these exams. The interesting thing is that while those with lower polygenic scores got relatively more CSEs or O levels, those with higher polygenic scores got more A levels, which are a level up, right? A level up in qualifications. The same thing if we look at people who stayed in school until at least what age, we see that those with relatively low polygenic scores and from low birthplaces, they are more likely to stay just until 16, right? They're forced to stay until 16, they stay until 16 and they drop out. While those with higher endowments, initial endowments, they tend to stay longer. So again, these are suggestive results, but they suggest, at least to us, that the reaction to the policy, the way different groups reacted to the requirement to stay in school until age 16 might play a role, right? Maybe the ones who, with better initial endowments, did more to differentiate themselves from their cohort, and that might have had a return in the labor market. The other thing that we looked at is in cognitive functioning. Again, this was measured when they were like in their 50s, 60s. They're not great measures of cognitive functioning, I have to say, but the hypothesis would be like they got more education, they went to work in better occupations, maybe they just got better cognitive functioning, and that's why they are seeing, better returns, and we see basically no evidence of that. But again, these results might be taken with a grain of salt because our measures of cognitive functioning in the survey are not great. And then I think these are kind of results that I'm pretty excited, and these are, I should say, these are yesterday night's results, the things that we just ran. And I'm especially interested in hearing your feedback on those. So I told you we have a subsample of siblings in this survey, right? So in this data. So what we thought it would be interesting to do is that in order to understand how much of these effects are coming from things that are related to family level factors versus within level factors, we thought we could use this sibling sample. So the way we're going to use this sibling sample is that we're going to run a two-stage square specification, but a bit different, without using the ROSLA. What we're going to do is that we're going to run the log wages on whether you were born, the post, whether you were born after September 1st, 1957, the score, interacted with the score, the post, the cohort trends, and and then we have those, kind of family fixed effects, right? The quality of a family. And the quality of a family might be loading on the polygenic scores, like the same way that I talked about the Kong et al. Paper, right? The quality of your family is also reflected on the scores. So what we did is that we instrumented for the post times the score and the score using the one's polygenic score minus the average polygenic score of his or her siblings in the sibling specification, in the sibling sample. So what this is saying is that we can, in this way, we have something that is related to our own PGS, but it's not related to this family quality thing. So this is a way to get at these interactions, hopefully subtracting any of these family common effects. And we find something that it's very interesting when we do that. So here are kind of the results. So the first columns gives you our results for our sample, the 10-year bandwidth, that shows that we have a significant reduced form interaction between the PGS and the post, and it's positive. Then we redo that with the sibling sample only, and you can note that the N drops a lot, right? We have much fewer siblings than we have unrelated people. So you can see that there we don't find a positive. It's a negative, but very small, and you can see that because of the larger standard errors, we can't really reject that they're the same. But the interesting part is that, again, we do the PGS for the first stage, instrumenting the polygenic score with the difference between the participant polygenic score and the average in their family. And again, we see a pretty strong first stage, meaning that that's a good instrument. And when we use this instrument on the log wages for the two-stage squares, we actually see a negative interaction between the PGS and the post. So I think this is a really preliminary result, and we still need to think carefully about them and see how robust they are. But I thought those were pretty interesting and worth discussing here, because what this suggests is that this effect of education in increasing these gaps might be coming from factors that are different between families, because within families we are seeing that, if anything, the reform is decreasing gaps in wages. So, if we think about channels, then channels such as, suddenly channels such as school quality and things like that are more likely to be playing a part here than before I saw these results, I think. So since I have a few more minutes, I'm gonna go. So another possible explanation for some of these results is that maybe, we're looking at different complier populations across different groups of initial endowments. And it might be that just, you know, the compliers are different, right? And that's why we're seeing different returns. So for just an example, is like, why would a person with high score, of high polygenic scores, be dropping out of school at age 15, right? It must be that they are facing larger environmental barriers, right? And how is that, you know, they might just be a different margin of complier, different margin of returns that we're estimating. So what I have here is by no means perfect, but what we did to try to get at that is to ask, you know, to do kind of a type of mediation analysis and ask if we control for a bunch of predetermined characteristics interacted with school leaving age, and do we see a difference in our baseline results, right? Do we see that these differences in characteristics of this across these different groups of endowment, people in different groups of endowment can be explaining our main results? And what we see, so the baseline are in the first column, and then kind of the predetermined characteristics. So the dependent variable is always log wages, and each one of the different columns adds a different predetermined characteristic. So the BMI polygenic score, leg length, male, England, Wales, being born in England or Wales. And what you can see is that, you know, adding all these predetermined characteristics do very little to our baseline results. Again, the main caveat here is that this is just interesting as interesting these predetermined characteristics are, and you might think they're not that interesting. But again, we're having this, the main interesting effect might be the RAG-EDU 15, and what we show is that when we add kind of both interactions together, they both survive. So I think it's less, it's kind of evidence against this idea that these differences in returns are coming from just the differences in complier population across endowment groups. So just to, you know, we have some, we do kind of a similar analysis for the SES outcomes that we have in the bank. They're not as great. We see qualitatively same results, you know, not as much power there as we would have expected. But I think I would rather just wrap up and see if there are any questions for discussion. So maybe I'll just go to my conclusion and see if you guys have any questions. So I think the main conclusion is that we look at this, you know, reform, compulsory school reform, these are very common around the globe. And when we look at the UK, we see that this reform, even though it equalizes quite a lot differences in educational attainment, it did not equalize differences in later life SES. We see that within our sample, the reform, if anything, increased differences in log wages across initial endowment groups. And when we look at the whole sample, when we look at bounds of how much equalization can have, we see that, you know, we can reject, you know, there's basically no evidence of equalization in either in our sample or in the whole sample. You know, possible reasons for why these results, you know, school quality might matter. So if you're forcing people to stay longer in school, those who are forced to stay in better schools gain more. It could be also that people from better initial endowments groups are reacting differently to the policy. Those are pursuing like further qualifications, they're staying longer in school, they're trying to differentiate themselves. So there might be a return to that. But I think what our conclusion is that, again, first we need to see how, you know, this is one type of compulsory schooling reform in one country, you know, in the UK. are our results generalizable? If they are, we should think that if really one of the goals of education and education policy is to address these SES differences, it might not be enough just to make people stay in school longer, right? You might need more evolved types of policies that address barriers to populations that are in the bottom of the distribution of these initial endowments. So I think I'm gonna leave it at that and see if you guys have any reactions. Especially to the sibling stuff, I would welcome thoughts on that. Thank you.
Thank you, Sylvia. I had a question for you.
Okay.
I guess a couple of comments. One is, you have some evidence that people who are initially relatively more advantaged also responded to the policy by acquiring more education, which I think there's an old paper in the US by Lang and Kropp, I think, that also found that the distribution of education shifts beyond the compulsory schooling minimum. And they made this argument that, you know, if everybody's going to graduate high school, well, now you need to, like, you know, do something else. So they argued that this was evidence for signaling. But I guess one implication of that is that it's not so clear to me that you want to limit your sample in the way you're doing for the entire analysis, because everybody seems to be affected by this reform. It's not clear how you you're limiting the sample using the outcome of the reform.
Well, we're limiting the sample, but only at people the school leaving age above 18, right? So we see effects. We don't see effects at 19. We don't see effects for college, and that's also true for other. If you look at other data sets that don't have the limitation that we have. So I don't think we are. By limiting in that way. I don't think we are. It's problematic.
But that's an ex-post assessment. You know, that's just something like you now looked at the data and you like see that there isn't anything. It's not an ex-ante assessment that these people were not going to be affected. So I don't know.
Right.
I mean, I don't know what it buys you to restrict the sample that way. I guess that
it's because we don't. It's going to be hard. It's how do we do the two steady square with school leaving age if we don't have school, right? We don't have. It's just a measurement limitation. We don't have school leaving age for the highly educated. So I mean.
Well, I mean, this brings me to, I guess, the second comment that I was going to make, which was that I think you're hinting at this at the end. Do we learn that education is not a great equalizer, or do we learn that compulsory schooling is not a great equalizer? Which is not kind of the same, because there could be alternative ways of inducing people to going to school that maybe would have different effects. So I guess this is something that I think about in my own research with looking at compulsory schooling, which is, are the benefits of forcing people to go to school the same as the benefits of attending school willingly and enthusiastically and voluntarily?
Right.
And I guess that maybe, I don't know. And so I guess maybe or maybe not, but I guess the question that I had for you is, how do you interpret in your data, are you suggesting your results are informative about education as a whole, or is it about compulsory schooling as the equalizer?
Yeah, I think it's education induced by compulsory schooling, right? So I think that's where my generalizability comment comes in, right? I think it would be important to do this, as you mentioned, in other types of education reforms. That said, you know, like that's one of the main types of reforms that's out there, right? So yeah, but I agree with you that the results might be very different if instead of restricting people's choice, you might be, you know, right? You might be the type of reforms that would increase the choice set instead of restrict the choice set might be very different, right? Types of policies that say reduce the cost of going to school might have very different effects than compulsory schooling reforms. So yeah, I take your point. So are you suggesting we change the title?
No, I don't know. I like the agenda. I think I think you're asking the right question. I just, given the results that you have, I think we may learn a narrower part of the answer.
Mm-hmm.
You know, it's a very ambitious question. I like that. I don't mean to suggest that.
Mm-hmm. Yeah.
Sorry, there's another question.
Okay. So where can you, I'd rather if people speak to me. I don't know where to get to look at the.
Hi, I didn't know if anybody else was waiting. So this is more a suggestion than a question, but as a sociologist, when I hear someone trying to create a numerical ranking for occupations, my first thought goes to occupational prestige or socio-economic index. Obviously, you can't do that on the fly, and I don't want to get you in trouble with your econ peer reviewers who might be more comfortable with something like median wages, but it would make a very nice appendix.
Yeah, we have done that. So actually
oh, you do?
It's something like socioeconomic socioeconomic categories in the UK. They're very, it's actually not hard because in the UK, they are so much into like this prestige, this occupation prestige, that it was actually easy to do. And so I presented, so the first version of this paper used that kind of thing, and we were finding similar results. And I don't know if I have it. I don't think I have it in my slides here today, but we're finding exactly the same results. But one thing, so I presented to an economics audience with these results with SAC, and they're like, but you are, I think the response that I got was, oh, but you have over 400 occupation categories. Why are you collapsing it? You're gonna have much more variation if you just like link to wages, and then the wages have a nice thing of being able also to interpret magnitudes, right? But for sure, the stack will be in the appendix. So yeah.
Excellent.
Yeah, thank you. Yeah. So there is one here. Another one is their work on what I found it now. Is their work on what a polygenic propensity for more education really captures? What are the mechanisms for this? Yeah, so that's kind of where I was trying to get. There is work, you know, and I think the idea is that it captures a lot of things. So I had this. Maybe it's worth going through the. How do I do this? I don't know. Oh yeah, through my. I had this thing of what it captures. Maybe it's worth going through this. I don't know if I.
Well, sorry to interrupt, Silvia. It's just that
I don't have time. Okay.
We're almost out of time, so
yeah. So maybe I won't go. Yeah, but
feel free to answer. I just think a lot of people have to leave, myself included. So I'm going to leave this open, and you can answer. But
okay. Yeah. So just to say that, yeah, the genetic variables, you know, kind of they do have a lot of things. They, you know, in this thing that I think you're still seeing, it captures like individual genetics, parental genetics, ancestry related mean differences, and any of these interactions of these genetics with environmental factors, right? So this is where I think we need to be very careful about how to interpret this. And I try in all my talks to be very careful about how we talk about this. It's definitely not a measure of cognitive skill, you know, purely. It's so much more than that. And that's where I think my analysis in the end was trying to unpack those, was trying to do sibling analysis and to do some of this other analysis to try to see where some of the pathways might be coming from. So absolutely, yeah.
I know we're over time. This is Aaron Panofsky. I'm wondering if I could ask a quick question about the polygenic score too.
Sure.
So the question I want to know is if you could talk a little bit about, so first of all, like, is it really exogenous as a variable, right? Because the way the polygenic risk score, like it's a correlation basically between the environment and whatever genes are in the individuals.
Mm-hmm.
And so why should we assume that this sample has the same sort of structure of environmental, the same distribution of environments and same distribution of genotypes into environments that the test sample has?
Yeah, no, that's a good question. We shouldn't, right? Like that's a very good question. The way we do it now is that we use a sample that is not our sample to run the GWAS, to run the correlations where we're gonna get those weights from, right? And then we're gonna plug these weights into our samples. So I guess what you're saying is that why should these weights be valid in our sample? And I guess the best question I have is that we see that, you know, once we plug these weights in our sample, we see that they're very good predictors. So I think you're right that, you know, if we could, in an ideal world, we had, you know, unlimited data, and we could run these GWAS into the same, you know, and then you had this unlimited data, and you randomly divide it into two, and then you run the GWAS in one part of the sample and you apply the PGS in the other part of the sample. That would be ideal, but I think we're not in this ideal world, and we use the data that we can, and I guess the fact that we have highly predictive scores, even though we are using, we're getting these weights from other datas, that suggests that there's at least some validity to the approach. So.
Right. Can I follow up just slightly? So,
yeah.
So then how do you, so, you know, there's that recent paper that Molly Jaworski led about, like, so it's the portability problem, that it's not only between ancestry groups, but it's within ancestry groups. And you know, so like, it's very technical. I don't totally understand everything about it, but I think it's because of sort of environmental heterogeneity.
Right.
And
yeah.
So like, how do you, so, and I was just struck by that first table that you showed, that Don commented on, where there's that negative correlation between the polygenic score, and I think, and you were going to check whether it was actually significant or not. But I mean, if that's a real slope, that would seem to suggest that it's predicting in a different way across the temporal cohorts.
Oh, you mean this one,
early on when you had the like 12 different charts.
Right, this one, yeah.
That one,
yeah.
B.
Yeah, I don't know if this, I mean, I need to check if this slope is even significant, but yeah. Yeah, no, it's a, you know, it's a, but that said, I have to say the PGS that we're using here is actually, a lot of the GWAS is coming from the UK Biobank.
Yes.
Because the UK Biobank is such a big player.
Yeah,
and we only, in our analytical sample, we only use 100,000 people, and there are 500,000 people. So 400,000 people are going to doing the GWAS. So, so it might not be that bad of a thing after all, but yeah.
Right. I guess it would.
It's a good, and it's something that I think the social genetics people are working all the time, especially when we talk about, you talked about portability. There is a lot of work now trying to make these polygenic scores fit other types of ancestry groups, right? Because it's so important right now. Most of the research is for European ancestry, and there's been a lot of work trying to learn about other ancestry groups and how we translate what we know to other groups. So
Right.
yeah.
Okay, thank you.
You're welcome. Thank you. They're good. So let me see if there's something else. If there's time, would you mind speaking a little about modular regression discontinuity technique you used and why and how it was appropriate? Thank you. Sure. Yeah, so the nice thing about the regression discontinuity, I have to say I'm a big fan of this method, is the just being so clear, right? So I think the ability to do graphs like this one, right? That you know, that you can see where the results are coming from. You can see, you know, that you have this big change in education, and well, not necessarily that big, but you have this clear change in education, and then years later you have the same pattern in wages. So I think that's the for me kind of the main why is it attractive? It's very intuitive. We have a threshold that is arbitrary, and then we see the data behave in a way that is consistent with the threshold, and then we see kind of effects on outcomes, right? So we see that these students born just days before the threshold and days after the threshold are similar in all this genetics and other predetermined characteristics, and then you see a difference in outcomes years later. So I think that's a big sell for me, you know, being able to very transparently look at the raw data and see the results. So I think this is the big, yeah. I don't know if you had another more question about RD, but that's why I like it so much. So I don't know if there are other questions. Let's see. I think that's it.
Yeah.
Okay.
Sylvia, I think most people are leaving because we're out of time.
Yeah. Thank you so much for staying. This was helpful. If you have any questions, or you feel free to email me again. This is very good to present this. I like to get it out, so it's good to say it out loud. So.
Could you put the slides on the CCPR webpage?
Sure. So if should I send it to Anna?
Yes.
Okay. I'll send it to Anna, and I'll add my contact information in case you have any follow-up questions. And thank you for the feedback. You know,
if you have text, either of this presentation or of something recent, if you could add that would be very helpful.
Sorry, something
If you have
recent.
text, if you have a paper.
Oh, a paper. Yeah, it's on the works. It's yeah. I think I'm gonna have it pretty. Like, we have a version, but I want to add more stuff to it. But yeah, once I have it, I'll send it to her also.
Yeah, when you have a paper on this, that would be helpful. And if you have any recent papers on the same topic.
Oh yeah, I do. Okay, I have a PNAS paper I can send. Yeah.
Send it all to Anna, and she'll put it all on the webpage. Thank you very much.
Yeah, that would be great. Thank you so much. Thank you for the opportunity.
Thank you.
Thank you, Sylvia.
Thanks. Bye.
Bye.